So today we're going to talk about DNA analysis and how it relates to our cases and what we can do to understand this material before we're actually applying it. So before we start, do any of the three of you have an undergrad in science?
I do.
What's your undergrad?
It was environmental science.
Oh.
So not super science.
Well, you were far ahead of most attorneys who have nothing. I had no background in science at all, but this is something that we can all understand, and we have to in order to apply it to our clients' cases. So this first slide is statistics that I got from the Innocence Project about DNA exonerations. There are 364 DNA exonerees to date. 130 of those DNA exonerees were wrongfully convicted of murder. 102 DNA exonerations involved false confessions. 180 of the DNA exonerees had the real perpetrators identified, and 137 of the DNA exonerees had the real perpetrators identified through a cold database hit. And the reason I wanted to put these statistics up here and give those to you is, one, to kind of show you how outrageous this is, that there were 364 individuals that were wrongfully incarcerated because of bad science or because the technology wasn't available at the time. I find that number to be absolutely insane, that someone would be spending so much time incarcerated for something that they didn't do. And another reason I wanted to bring this up is to show you that the work that you're doing and the work that KIP does actually matters. That one individual that we can get out of jail to prove that they were wrongfully convicted is worth all of this, is worth all of the work that you put in, all the hours, all the frustration that is put into these cases, absolutely worth it. KIP has their own DNA exonerations. These are from the website. When you come for the exoneree day on the 22nd, hopefully you're going to be able to meet some of these individuals. We're still trying to set up who is going to be there on that day. But if you look at the year that these crimes were allegedly committed and how many years they actually served, you'll get 104.5 years. So these individuals spent a combined 104.5 years in the jail for things that they did not do. And I think Suzanne had said that she had done the math on what it cost the state to incarcerate these individuals for that amount of time, and how
$2.5 million. Actually, it'll be over $2.5 million, but just for the 104 years that they served.
Yeah. So I just find that to be absolutely incredible. So what are we using this DNA profiling for anyways? The first thing up there is that it's establishing a probative link between the evidentiary DNA and that of the possible offender's DNA. So this is what the prosecutor is trying to do. They're trying to claim that whatever DNA was found on the scene is going to link to our client. What we're trying to do is the complete opposite, is to exclude our client as a possible contributor to that DNA sample. DNA profiling has gotten so advanced that they can determine whether it's human or non-human, and they can identify the species if it's not a human DNA sample. The other thing that they can do now is to determine the number of contributors to a DNA sample. So a DNA sample might not be straightforward. There might be 2, 3, 4, 6 individuals that have contributed part of their DNA to one sample, and they can find out now how many individuals are for one sample. They can determine whether the sample came from a female or a male, and they can also determine the genetic relatedness between people. So this is seen a lot in the paternity testing. I cover a child support contempt docket, so in Kentucky you can get thrown into jail for not paying your child support, but before they can establish that support, they have to establish that this individual is actually the father of the child. So they will always have to do some sort of DNA testing to make sure that they're getting the child support from the right individual. So what is DNA anyways? I think most of us, when we hear DNA, we think of that image, the double helix. But for our purposes, we have to go one step further than that. We have to understand that each nucleotide of DNA has 3 components. One is a sugar molecule, a phosphate molecule, and then one of these 4 nitrogen bases. So if you look at that that image over there, you'll see that cytosine and guanine, I think is how you say it, will always match up together, and then the A and the T will always match up together. And the sequence and the repetition of those four will be the basis for our pattern of DNA. So another way to think about this is in terms of music. So I was a music minor in college, and if you know anything about music, there's always 8 notes per scale, right? Then you can't go outside of those 8 notes. You can do a sharp or a flat, but you have those 8 notes. The way you sequence those notes, the way that you use them, is going to determine what type of music that you get. So even if something is in the same key, say you have an F major key, that is Bizet's Carmen, right? It's a classic operatic piece of music. But if you take those same notes and flip them and put them in a different order, you can get Beyonce's Crazy in Love. And when you hear one or the other, you know for certain, oh yeah, that is Beyonce's song. It's not, this operatic piece of music. But it depends on how you sequence those notes. And it's the same thing with this DNA. If you have those sequences in a different order, that can mean that it's one person over another. So where is DNA found? Now there's going to be a very important distinction between these two and what we can use both of these for. So nuclear DNA is found in the nucleus of the cell, whereas the mitochondrial DNA is found in the mitochondria. That makes a lot of sense. They also have a difference in their shape. So if you look at that picture over there where it says chromosome, the shape is very linear and it's open-ended, whereas the shape of the mitochondrial DNA is always going to be in rings. The size is also different between the two. So in nuclear DNA, there's 46 chromosomes that contain 3.3 million nucleotides, whereas the mitochondrial is 1 chromosome that contains 16,569 DNA base pairs. One very important thing is the heredity of this type of DNA. If you have nuclear DNA, you're getting that from both your mother and your father. So 46 chromosomes, that means you're getting 23 from your mom and 23 from your dad. If you take a DNA test like 23andMe, that's where they're getting that number from, because they're trying to determine mother and father, right? Whereas if you have mitochondrial DNA, it's only coming from your mother's side. So that's the only thing that they can look for is the heredity from your mother's side of the family. Nuclear DNA contains 2 copies per cell, whereas mitochondrial DNA has 100 to 1,000 copies per cell. Another important distinction is that all nDNA strands contain an identical genetic material, whereas mitochondrial DNA can differ amongst locations in the cell or even within the same cell. And in order to find nuclear DNA as opposed to mitochondrial DNA, we're going to use different testing. So we're going to talk about that a little bit later on how we're going to test these different types of DNA. The major difference between the two is what is known as the DNA profile. So an nDNA profile consists of 26 alleles exhibited at 13 predetermined locations on a DNA strand. And we're going to talk about exactly what that means in just a second. But a mitochondrial DNA is a list of differences between 2 separate regions of the cell, known as HV1 and HV2, as compared to the sequence called CRS. So we're going to talk about this a little bit in depth. It may not make a lot of sense right now, but so the first thing you need to know about the difference between the two is if nDNA is available, that's what you have to test first. That will give you a more precise analysis, and it also gives you access to a bigger database to figure out who, what individual that DNA belongs to. So mitochondrial DNA is extremely important, and it's a new advancement because it has, we're allowed to test things that we were not able to test before. So one is if the nuclear DNA is not available, you can try to use mitochondrial DNA to get that testing done. So this can happen in old remains or evidence such as hair, bones, teeth, things that may have decayed a little bit. If the evidence is not suitable for STR analysis, we're going to talk about what that is. You can use mitochondrial DNA analysis. Mitochondrial DNA is also used when the sample is small, damaged, or degraded. And this is extremely important because a lot of our cases have very, very old samples. So if you have a very old sample, you might not have the nuclear DNA available, but you may have the mitochondrial DNA that you can test today. Another important use for mitochondrial DNA is that if the victim or the suspect is deceased, missing, or unavailable, you can get a single maternal relative to provide that sample, and this is very helpful in cold cases. But there are some downsides. So unlike nuclear DNA, it's not specific to one individual. Rather, you are finding a specific family or a racial subpopulation rather than just that one single person. And the databases for the mitochondrial DNA and the nuclear DNA are very, very different. So how did we get to where we are today? Between the 1920s and the 1970s, the way that they were using DNA, or I'm sorry, they were trying to identify people was through blood type, through serology, which is the testing of blood serum, or by looking at bone marrow matching. So that's how they were trying to identify two people or to link them paternally. In the 1980s is when we start getting these developments in DNA testing, right? So in the 80s, Alec Jeffreys developed this RFLP method. And anything that's in red, we're going to talk about in just a few slides. So this is basically just talking about our timeline first before we go into how these methods work. In 1981, they started looking at mitochondrial DNA. And they used this method called the CRS. In 1983 was the PCR, which they developed in order to fix some of the shortcomings and downfalls of this RFLP that was developed just a little bit earlier. In 1986, they began using DNA analysis in the criminal justice system. So before 1986, a lot of the DNA analysis was used to find genetics, to determine what was going to be inherited from the mother to the child, defects, things like that. They were using it in medicine more than the criminal justice field. So finally, they decided that this might be helpful for people that are convicted of crimes where their DNA may be on the scene. A year later is when the U.S. started using DNA profiling in the criminal justice system. But it wasn't until '89 that the DNA evidence was actually used to exonerate an individual. So it took a little bit of time to get that first exoneration. Then in 1991, they started using this method called the STR, or the short tandem repeat method, which was the new and improved way to do DNA testing. And this is still what we use today. So it's a fairly new type of procedure. Are you guys 90s babies? So you're just as old as this method, right? In 1992 and 96, the FBI decided that they were going to start studying mitochondrial DNA and conduct their own testing. In '94 was when the FBI developed what they called the Combined DNA Index System, or CODIS, which is the forensics database that they can use to kind of plug in a DNA analysis and see if it links to any individuals in the system. And in 2009, coming back to Kentucky, that's when Kentucky law required that all individuals that were convicted of a felony offense had to submit a DNA sample. So that's going to be, we're going to talk about that a little bit later at the very end of the presentation, but I wanted to throw that in there so you can see where Kentucky falls in this line.